In this lecture, we take a Möbius transformation f and four distinct complex numbers z sub 1, z sub 2, z sub 3, and z sub 4. We are going to show that the cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4 is equal to the cross ratio of f of z sub 1, f of z sub 2, f of z sub 3, and f of z sub 4. We split up the exercise into two main cases. In the first case, all the z sub i's and all the f of z sub i's are finite complex numbers. In case 2, all the z sub i's are still finite complex numbers, but this time one of the f of z sub i's is the point at infinity. Without loss of generality, we take f of z sub 4 to be the point at infinity. We can include a third case, which is almost a corollary of the second case. In the third case, instead of the point at infinity being one of the f of z sub i's, it is one of the z sub i's that is the point at infinity. This really is an extension of the theorem, which only requires that the z sub i's be finite complex numbers. Case 3 extends the domain of the Möbius transformation to the extended complex plane. Without loss of generality, we take z sub 4 to be the point at infinity. The cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4 is equal to the fraction z sub 1 minus z sub 3 over z sub 1 minus z sub 4 times the fraction z sub 2 minus z sub 4 over z sub 2 minus z sub 3. And here's the cross ratio of the f of z sub i's. For the proof of case 1, we simply calculate each component of the cross ratio of the f of z sub i's. Because f is a Möbius transformation, we should be able to write f of z in the form the quantity a times z plus b divided by the quantity c times z plus d, where a, b, c, and d are complex numbers, and ad minus bc is not equal to 0. We start with f of z sub 1 minus f of z sub 3. f of z sub 1 equals the quantity a times z sub 1 plus b divided by the quantity c times z sub 1 plus d. f of z sub 3 equals the quantity a times z sub 3 plus b divided by the quantity c times z sub 3 plus d. We combine these fractions and factor out the result. We obtain similar expressions for f of z sub 1 minus f of z sub 4, f of z sub 2 minus f of z sub 4, and f of z sub 2 minus f of z sub 3. And so dividing f of z sub 1 minus f of z sub 3 by f of z sub 1 minus f of z sub 4, ad minus bc being non-zero cancels out. Z sub 1 minus z sub 3 should end up in the numerator. Z sub 1 minus z sub 4 should end up in the denominator. c times c sub 1 plus d is non-zero since f of z sub 1 is finite, so c times c sub 1 plus d also cancels out. c times z sub 3 plus d should end up in the denominator. c times z sub 4 plus d should end up in the numerator. Therefore, f of z sub 1 minus f of z sub 3 divided by f of z sub 1 minus f of z sub 4 equals this expression. We obtain a similar expression for f of z sub 2 minus f of z sub 4 divided by f of z sub 2 minus f of z sub 3. Like c times z sub 1 plus d, c times z sub 4 plus d, and c times z sub 3 plus d are non-zero and should cancel out. What we have left is just the cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4. And we have the proof for case 1. In the proof for case 2, f of z sub 4 is the point at infinity. We interpret the cross ratio of f of z sub 1, f of z sub 2, f of z sub 3, and f of z sub 4, which we are assuming is infinity, as the limit of the cross ratio of f of z sub 1, f of z sub 2, f of z sub 3, and f of z, as z tends to z sub 4. We focus on f of z sub 2 minus f of z divided by f of z sub 1 minus f of z. f of z sub 1 divided by f of z and f of z sub 2 divided by f of z will both tend to 0 as z tends to z sub 4, because f of z will tend to infinity. And so we'll be left with minus f of z divided by minus f of z, whose limit is 1. And so the cross ratio of f of z sub 1, f of z sub 2, f of z sub 3, and f of z sub 4 is equal to f of z sub 1 minus f of z sub 3 divided by f of z sub 2 minus f of z sub 3. Next, we determine a more precise formulation for f of z. In another video lecture of ours, whose title is Möbius transformations involving the point at infinity 1, we had derived a formulation for f of z where f of z sub I for one of the z sub i's is infinity. We have included a link to that video in the description of this video lecture. We applied the same strategy to derive the formula for f of z when f of z sub 4 is infinity. If f of z sub 4 is infinity, then f of z can be written in the form the quantity a times z plus b divided by the quantity z minus z sub 4. As in case 1, we proceed to calculate f of z sub 1 minus f of z sub 3 and f of z sub 2 minus f of z sub 3. F of z sub 1 equals the quantity a times z sub 1 plus b divided by the quantity z sub 1 minus z sub 4. And f of z sub 3 equals the quantity a times z sub 3 plus b divided by the quantity z sub 3 minus z sub 4. This factors out into this expression. Similarly, f of z sub 2 minus f of z sub 3 is equal to this quantity. Dividing f of z sub 1 minus f of z sub 3 by f of z sub 2 minus f of z sub 3, a times z sub 4 plus b is non-zero, so that it should cancel out. Now, why a times z sub 4 plus b is non-zero is because it is actually minus the discriminant ad minus bc. The discriminant, of course, is non-zero. Z sub 4 minus z sub 3 is also non-zero since the z sub i's are finite and distinct, and so should cancel out. And so we are left with the quantity z sub 1 minus z sub 3 divided by the quantity z sub 1 minus z sub 4 times the reciprocal of this fraction. This gives us the cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4, thus completing the proof for case 2. Case 3 is really the flip side of case 2. This time, the f of z sub i's are finite, while z sub 4 is the point at infinity. Let's start with the cross ratio of the f of z sub i's. In another video that we had prepared, the title of which is Möbius Transformations Introduction, we had shown that the inverse of a Möbius transformation exists and is also a Möbius transformation. We have also included a link to that video in the description of this video lecture. So, we apply f inverse to each of the f of z sub i's. By case 2, since f inverse is a Möbius transformation, this should equal the cross ratio of the f of z sub i's. That is before the application of f inverse. F inverse and f cancel out. So we end up with a cross ratio of z sub 1, z sub 2, z sub 3, and z sub 4. And we have the proof for case 3.